Welcome to Quantum Computing course. Moore's law says that the number of transistors in our computers double every 2 years. In order to make this happen, we need to make transistors ever smaller and smaller. And currently, so if we take a transistor, then its depth now is less than 50 atoms. So it's clear that now we're heading towards a problem. So as we make transistors smaller and smaller, invariably we will hit the one atom limit, and the rules of the game will change. A single atom behaves in totally different ways than a large collection of atoms. A single atom behavior is governed by quantum mechanics. Whereas when we have large collections of atoms, quantum mechanical effects will average out and will in general not be noticeable. Quantum mechanics is strange and counterintuitive. As species, we never really face quantum mechanics in our everyday life. And our brain is simply not wired for quantum mechanics. Even though we have now solid foundations of quantum mechanics in terms of its physics and mathematics, there are still many problems in quantum mechanics that are beyond our reach. The first direct manifestation of quantum mechanics that we discovered was spectral lines in radiation of various molecules. This is how we know now chemical compositions of stars, for example. For the atom of hydrogen, we have a very good theory based on Schrödinger equation that allows us to compute what are the energy levels and the spectral lines in radiation of hydrogen. And it turned out that even for moderately sized atoms and molecules, computations of energy levels require a lot of computer resources. Even armed with supercomputers, we find it extremely challenging to compute energy levels of various quantum mechanical systems. Yet, nature is able to do this easily and without fail. In 1980, Russian mathematician Yuri Manin suggested that instead of fighting quantum mechanics, we could use quantum mechanical systems as computational devices. Manin had created a paradigm for quantum computing that we use today. About the same time, a physicist, Paul Benioff, suggested a quantum mechanical model of a Turing machine. In 1982, American physicist Richard Feynman popularized the idea of quantum computing. Throughout the 80s and early 90s, the area of quantum computing was considered to be a niche branch of computer science, and very few people worked in it. Maybe we should mention the name of David Deutsch, who laid some foundations of this field. And then the game radically changed in 1994, when Peter Shor had discovered an algorithm for a quantum computer that will break RSA encryption. So the RSA encryption scheme is one of the main tools that we use today to secure our internet communications. So security of RSA encryption is extremely important for the internet infrastructure. This course on quantum computing will be multidisciplinary. So here we will have components in physics, mathematics, and computer science. I'm going to incorporate the foundational ingredients from all three areas into this course. But of course, strong background in these areas will definitely help. The first lecture in this course will be introductory. So we will give an overview of the whole course using very broad strokes. The first fundamental notion of quantum computing is that of a qubit. So let us try to understand what a qubit is. So imagine that we look at the spin of an electron. Well, an electron will have an electric and magnetic field, and the spin describes magnetic properties of an electron. So an electron behaves like a little magnet. And so the spin of an electron could be has a direction, and suppose we have a certain axis in space, so for example vertical axis, and we could have an electron with a vertical direction of the spin. We will also use a notation borrowed from physics to denote the state of an electron with vertical spin in this way. So this is state of an electron with a vertical spin. There is also another state where the spin of the electron points down in vertical direction, right? So now, we get two states that we're going to call two basis states of an electron. And the idea of a qubit is to tie this with computer science. So this means that this basic state of an electron we will interpret as 1, and the down state of an electron will interpret as 0. Or rather, maybe we will also write it like this. So this is just a matter of computer science interpretation. So now we parameterize our basic states of an electron with bit values. So one state corresponds to value 1, and another state corresponds to value 0. But then, of course, there are states of the spin of an electron which is not necessarily pointing up or down, so it could point at an angle. And quantum mechanics tells us that general state of the spin of an electron can be described as a linear combination of an up state and a down state, where A and B are complex numbers, and they satisfy the equality that the norm of A squared plus the norm of B squared is equal to 1. This description of the physics of the spin of an electron gives us the idea of a qubit. A qubit is a vector which is in two-dimensional space, right? So we have a two-dimensional space. Well, this is C2 because we will work with complex numbers. And here we have two basic states. So these two basis vectors are going to be called 0 and 1. And a general qubit psi will be a vector on this space. And so a qubit is an expression A times 0 plus B times 1, where A and B again satisfy this condition. So norm of A squared plus norm of B squared is equal to 1. And A and B are complex numbers. In other words, qubit holds not just a single value, but a linear combination of both values. So whereas classical computers work on deterministic principles, so here every unit of memory either holds the bit value of 0 or the bit value of 1. In quantum computing, we depart from this paradigm. We are going to hold both 0 and 1 values simultaneously, but this is going to be a weighted sum. So this state could be more 1 than 0, or more 0 than 1, or could be some equal combination of 0 value and the 1 value. Now, let us see what happens when we have a particle interaction. Suppose we have not a single electron now, but a pair of electrons or a pair of interacting electrons. And we are looking at their joint spin states. So let's look at joint spin states for a pair of electrons. So pair of interacting electrons. So here, so what we could have is we could have the following basic states. So where both electrons will have spin up, or we will have first electron has spin up and the second electron has spin down. Or we could have the first electron with spin down, the second electron with spin up, or both could have spins down. These four states are just the basic states of this system of a pair of electrons. And a general state is going to be a superposition of these states. So we can write it as a linear combination. So A0 times double down plus A1 times down up plus A2 times up down plus A3 up up. So what will be the computer science interpretation of this construction? Now this gives us something that is called a 2-qubit. So here, using that interpretation as up state as 1 and down state as 0, so this linear combination will be written as A0 times 0, 0 plus A1 times 0, 1 plus A2 times 1, 0 plus A3 times 1, 1. And so here, all these AIs are going to be complex numbers. And with the condition that the sum of their squares of their norms is going to be normalized to 1. So this is what is called a 2-qubit. And we can see that 2-qubit holds a linear combination of all possible classical values of 2 classical bits. Right? So there are 4 different combinations for the values of 2 bits. And a 2-qubit holds all of them at once. Now it becomes clear how to go from a 2-qubit to N-qubit. So here we have basic states that are strings of 0 and 1s. So where we have n-bit expressions here. To simplify notations, we are going to use integers in their binary form. And so we're going to denote this thing by k, where k here is an integer. And so, for example, if n is equal to 4, then and we take k equals 9. So what is this state 9? Right? So what we do is we use a binary expansion of 9. So 9 is 8 plus 1, right? So which is 2 cubed plus 2 to the power of 0. So the binary expansion of 9 is going to be 1, 0, 0, 1. And so when we write 9, so this is actually what we are going to mean. right? So this, in terms of spin of an electron, this is a state of 4 interacting electrons, where the first one has spin up, then 2 electrons have spin down, and the last electron also has spin up. So now an N-qubit can be written in the following way. So we can use the summation notation. So it's going to be sum, k goes from 0 to 2 to the n minus 1, ak times the state k. And again, this state k is interpreted as a binary n-bit integer, with the constraint that the norm of this vector is equal to 1. So the sum k goes from 0 to 2 to the n minus 1 norm of ak squared is equal to 1. And so ak's here are complex numbers. So this means that this psi is a vector in the space of over complex numbers of dimension 2 to the power n. So this tells us that the complexity of an N-qubit grows exponentially with n. And so if we have n interacting electrons, then in order to describe the joint state, we need to store 2 to the power n complex numbers. And even when n is equal to 50, this is far beyond our reach with a computer. This explains our difficulties in solving problems for energy spectra of atoms and molecules, because it's very easy to imagine a molecule with 50 electrons, and we see that describing the joint state is beyond our memory capability for computers. Yet, nature has no problems with operating with 50 electrons and generating spectra of complicated molecules. Now, what's the catch here? If N-qubit has such a huge internal memory capacity, why are we not dropping our classical memory chips and switch to quantum devices for storing information? The answer to this is that the main issue with quantum mechanical systems is that quantum mechanics is probabilistic. So we have an issue here with accessing information stored in quantum mechanical system. With the classical computer memory, if we stored an n-bit expression, then later on we can retrieve the same expression from the memory. It doesn't work like this with quantum systems. Given a quantum state like this, we cannot retrieve the values of the coefficients ak's. The only way how we can access information written in this quantum state is using measurements. So we have a quantum state, and we can perform a measurement on this quantum state. And the result of a measurement of a quantum state, which is a superposition of classical states, is going to be a single classical state. And the outcome of the measurement is probabilistic. So this means the following. So when we measure the value of psi, or the value stored in psi, then we get one of classical values k, but we obtain this result probabilistically, so with probability which is equal to absolute value of ak squared. Right? So here we have a weighted sum. So some values of k could be weighted more heavily in this sum, and some values of k could be weighted less. So here the outcome of a measurement is going to be probabilistic. So this means that we will read off a value of k with probability which is equal to the square of the magnitude of the corresponding coefficient. So if we have several identical quantum states, then when we perform measurements of them, we very well might obtain different values. So with N-qubit, on one hand, we have a huge amount of information stored in this qubit. But on the other hand, we have a really hard time accessing this information. And so we can only get some answers probabilistically, and we cannot read out the full information stored in this qubit. So what is a quantum algorithm? A quantum algorithm is a procedure that has an input and an output. And so we have some input state. So for example, this could be a state that corresponds to an integer that we would like to factor. And so we take this input and transform it. We apply some transformations to this quantum state. So physically, this could be shining lasers at this quantum system. And we get a new quantum state, which is some mixed state. So this could be the sum. K goes from 0 to 2 to the n minus 1, ak times k. And so then, after we obtain this state, we perform a measurement. And we obtain one state as the outcome of a measurement. And the challenge of the quantum algorithm is to organize this quantum computation in such a way that with a high probability, we obtain the answer that we seek. So for example, so this state could incorporate information about two factors of an integer m that we want to factor. So this whole procedure is probabilistic. So this means that if we run quantum algorithm twice, we are not guaranteed to get the same answer at each run. But what is required is that we get the correct answer with a high enough probability. And if, for example, this is the question about factoring large integers, then we can always use our classical computer to verify whether the answer that we obtained is correct or not. So we can take two factors, multiply them together, and check whether the result is equal to m. As you can imagine, designing quantum algorithms is an extremely challenging task. And so here, at this time, we know only a handful of useful quantum algorithms. And we certainly want to develop the theory of quantum computation better so that we have more quantum algorithms that can do useful things. So here we have a great potential for this. So we know that quantum bit has a huge memory capacity. And so there is a huge potential for new, interesting, and powerful quantum algorithms. But we need to work really hard to discover new quantum algorithms that will solve interesting and hard problems. We have also have clear difficulties with building quantum computers. So this is an extremely challenging task. Most quantum computers operate at very low temperatures, like fraction of a Kelvin. And in this course, we will also discuss technological challenges for building quantum computers. But again, so recently there was a lot of important progress, but there is a long road ahead of us. I will not be providing typed notes for this course, but I wanted to mention that there is a book that I wrote, so Quantum Computing for high school students. A couple of years ago, I taught a version of this course for a group of high school students. So clearly, so this was not the same course, but a much simplified version of the university level course. So yet there is some overlap, and so maybe there is more detailed explanation of certain background topics that you can find in this book, but which will not be in the course, right? So this is written by me, and so in the description you can find a link to this book. So the electronic copy of this book is freely distributed on internet, so a paper version of this book is available for purchase from places like Amazon. In this introductory lecture, we gave a very compressed overview of what's going to be in this class, and our goal of this course is to understand really well Shor's algorithm for integer factorizations using quantum computers. So we're going to study this and all the background topics that are required for this. So there will be bits of quantum mechanics, computer science, mathematics, linear algebra, cryptography, and so we will discuss various topics in quantum computing, and we'll go beyond Shor's algorithm.